In the vast, silent theater of the cosmos, a ghost particle dances just beyond our sight, a whisper in the fabric of reality itself. For nearly half a century, it was a mathematical phantom, a theoretical ghost haunting the equations of our most brilliant minds. Its existence was the key to everything, the answer to a question so fundamental it shakes the very foundations of our universe. Why do things have mass? This is the story of the man who dared to chase that ghost, a quiet, unassuming physicist whose one flash of insight would change the world forever. His name was Peter Higgs, and this is the tale of how he unveiled the secret of mass. Our story begins not in a gleaming, high-tech laboratory, but in the drizzly, intellectual heart of Edinburgh in the 1960s. The world of physics was in a state of beautiful chaos. Scientists had a stunningly successful theory, the Standard Model, which described 3 of the 4 fundamental forces of nature with breathtaking accuracy. It was a masterpiece, a cathedral of equations. But it had a fatal flaw, a gaping hole right in its center. The model's equations worked perfectly only if every fundamental particle, the electrons, the quarks, everything had no mass at all. 0. Which is, of course, completely absurd. We exist, we have mass. The chair you're sitting on, the planet beneath your feet, the stars in the sky, they all have mass. The Standard Model, for all its genius, was fundamentally broken. It described a universe that couldn't exist. Physicists around the globe were stumped. It was like having a perfect blueprint for a car that showed no engine. How did the universe get its stuff? How did particles, born massless at the Big Bang, acquire the property we call mass? Enter Peter Higgs. He wasn't a flamboyant celebrity scientist. He was a quiet, thoughtful man, known more for his methodical thinking than for headline-grabbing pronouncements. While others tried to patch the Standard Model with complicated fixes, Higgs took a step back. He wondered if the problem wasn't with the particles themselves, but with the space they moved through. Imagine walking through an empty room. You can move freely, without resistance. Now, imagine that same room is suddenly filled with a crowd of people. Moving through it becomes much harder. You have to push your way through, interacting with the people around you. You feel heavier, more sluggish. This, in a beautifully simple analogy, was Higgs's revolutionary idea. He proposed that the entire universe, every cubic centimeter of empty space, is not empty at all. It's permeated by an invisible, universal energy field. He called it, simply, the field. Particles moving through this field would interact with it. The more strongly a particle interacted, the more drag it would experience, and the more mass it would appear to have. A particle, like a photon, the particle of light, wouldn't interact with the field at all, so it would zip through space at the speed of light, massless. But other particles, like the quarks that make up protons and neutrons, would interact strongly, acquiring significant mass. It was an idea of breathtaking elegance and audacity. It meant that mass wasn't an inherent property of a particle, but a result of its interaction with this cosmic molasses, this invisible field that fills all of reality. Higgs wrote down his idea in a short, 2-page paper in 1964. And what happened next is the stuff of scientific legend. The first journal he sent it to, Physics Letters, rejected it. The editors thought it was interesting speculation, but had no obvious relevance to physics. Can you imagine? Rejecting the paper that would one day win a Nobel Prize. Undeterred, but slightly disheartened, Higgs added a crucial paragraph. He reasoned that if this field existed, it must have a particle associated with it, a telltale ripple, a clump of energy that could be excited out of the field. This particle, a manifestation of the field itself, would be the smoking gun. He sent the revised paper to a different journal, Physical Review Letters, where it was finally published. The hunt for what would become known as the Higgs boson had officially begun. But a theory is just a story until it's proven. And proving Higgs's idea was a challenge on a scale humanity had never before attempted. The Higgs boson, if it existed, was predicted to be incredibly massive and ridiculously unstable, decaying into other particles almost instantly. To create it, you would need to smash particles together with unimaginable energy, recreating the conditions of the universe a fraction of a second after the Big Bang. You would need the biggest, most powerful machine ever built by human hands. For decades, the idea remained in the realm of theory. Physicists built bigger and bigger particle accelerators, smashing atoms with increasing ferocity, sifting through the debris for any sign of the elusive particle. They found nothing. Years turned into decades. A generation of physicists spent their entire careers searching in vain. The Higgs boson became a kind of holy grail, so elusive that Nobel laureate Leon Lederman nicknamed it the God particle, a name Higgs himself famously disliked. He felt it was misleading and sensational. To him, it was just the boson. The world watched and waited. Doubts began to creep in. What if Higgs was wrong? What if the whole Standard Model was a dead end? The fate of modern physics hung in the balance. Finally, the world's physicists pooled their resources to build the ultimate discovery machine, the Large Hadron Collider, or LHC, at CERN in Switzerland. A 27-kilometer ring of superconducting magnets buried 100 meters beneath the French-Swiss border, designed to accelerate protons to 99.9999991% the speed of light and smash them together, creating billions of collisions every single second. The LHC switched on in 2008, and the data began to pour in. It was a torrent, a digital avalanche that required a global network of supercomputers to analyze. Scientists worked around the clock, sifting through the subatomic wreckage of trillions upon trillions of collisions, looking for a very specific signature, a tiny bump in their graphs, an excess of certain decay products at a particular energy level. It was like looking for one specific grain of sand on all the beaches of the world. And then, on July 4, 2012, nearly 50 years after Higgs had first proposed his idea, the moment arrived. In a packed auditorium at CERN, with a frail, tearful Peter Higgs sitting in the front row, the leaders of the two main experiments, ATLAS and CMS, presented their results. They had found it. A new particle, with properties consistent with the predicted Higgs boson, at a mass of around 125 gigaelectronvolts. The room erupted. Physicists, who had dedicated their lives to this search, wept and embraced. The missing piece of the Standard Model had been found. The ghost had been caught. The following year, Peter Higgs, along with Francois Englert, who had independently developed a similar theory, was awarded the Nobel Prize in Physics. It was the ultimate vindication of a lifetime of quiet conviction. But here is where our story takes its surprising turn. We've been told that the Higgs boson gives mass to other particles, and it does. But the shocking secret, the twist that redefines our understanding of ourselves, is that the Higgs field is only responsible for a tiny fraction of the mass we experience every day. The mass of the fundamental particles, the electrons and quarks, comes from the Higgs field. Yes, but those fundamental particles only make up about 1% of the mass of the atoms that build you, me, and everything we see. So where does the other 99% of mass come from? The answer lies in the most famous equation in all of science. E equals mc. Energy and mass are two sides of the same coin. Inside the protons and neutrons that form the nucleus of every atom, tiny quarks are buzzing around at nearly the speed of light. They are bound together by the strong nuclear force carried by particles called glue. The vast majority of your mass, the stuff that gives you wet, isn't from the stuff of the quarks themselves. It comes from the colossal kinetic energy of their motion, and the immense potential energy locked within the gluon field that binds them together. Your mass is not solid substance. It is frozen energy. You are a swirling, buzzing construct of pure energy, condensed into matter, according to Einstein's legendary formula. The Higgs field provides the seed mass for the fundamental bricks, the quarks, but the vast, towering skyscraper of your own body is built from the energy that holds those bricks together. The Higgs boson didn't just solve one mystery. Its discovery pointed us toward an even deeper and more profound truth about the nature of our own existence. We are not just matter. We are energy, forged in the heart of the atom, given a final touch of substance by a ghostly field that pervades all of space and time. The secret of mass wasn't one secret, but two, and the universe, it turns out, is far more strange and beautiful than we ever imagined. Thanks for watching. If you were as fascinated by this journey into the heart of matter as I was, don't forget to like, subscribe, and hit that notification bell for more stories from the frontiers of science.